Let's see. All right, let's see. Let me be sure I'm recording. I'm recording. I haven't checked my audio today. Let me, it's testing. Okay. All right. So, scoot that over a little bit. Covers about everything. All right. Okay, I guess we better get started. Today we're going to do a review on chapters 3 and 4 in preparation for exam number 2. That's due on Thursday. So let me get my documents out here. Just review. Okay. First up, anybody have any specific problems that we need to deal with before I start talking? No problems? Well, okay. We'll just take the review document, and I've got some important problems I think that we ought to cover. So I'll start off, and you interrupt me if you think of something that you need to have dealt with. All right. Number one. Number one, and this is chapter 3, number 1. That's weird about this particular document. The chapter 4 review start renumbers, and I never have gotten around to fixing that. So this is chapter 3, number 1. Naturally occurring copper exists in 2 isotopic forms. This one and this one. The atomic mass of copper is 63.55 atomic mass units. And when we say atomic mass, we mean the weighted average of naturally occurring copper, as opposed to mass number, which is simply the summation of protons and neutrons for any isotope. Oh, there's Stormy. Better let her in. Okay. So how we go about doing the weighted average? Well, actually, this problem is working backwards in one respect. The weighted average is 63.55 atomic mass units. So that's the information that we're given. And the question is, what's the approximate natural abundance of this one, 63, the isotope 63? So normally what you do is you take, if you're not given the atomic mass for the individual isotope relative to carbon-12, then you work from the mass number. So if we were to say the naturally occurring abundance of this is some x, and I'm going to use x as the decimal value for, not the percent, but the decimal. And we multiply that times 63. Okay. Then this one would be multiplied by 65. But what is its natural abundance? Right? Well, we only have 2 isotopes. So if this is one fraction, then this has to be what's left over, right? 1 minus x. Okay, so there our problem is set up. We take the fractional abundance of this one times its mass number, fractional abundance of this one times its mass number, add them together and you get that. So the equation is going to be this plus that equals that. Okay? So now, what do I say over and over and over again? If you got one equation in one unknown, you can solve it. So this would just be 63x, and this would be 65 minus 65x equals 63.55. Okay. Well, I might as well do it. So you combine the numbers that have no unknowns, the whole values, 65 and 63. So this becomes a negative on that side. And this, added to a negative that, is minus 1.45. So we take this and put it over here. You get that value. Then if you combine these two, this is a positive 63 and negative 65 minus 2x. Okay? So we solve for x. That's a negative, that's a negative. So when you divide both sides by a negative 2, your value becomes positive. And this was 0.725. So x equals 0.725 or 72.5%. And let's see. All right, so something else I also say, in multiple choice tests, if you don't find the number if you know you've done the problem right, and you don't find your answer exactly as you determine it in the choices, then you pick the best answer. And the best answer in this group is 70%, or C. Okay. If there had been another choice, say none of the above, then you pick that one because you got that and it's not there. But since you have values for every A through E, then you pick the best one. Okay. Let's see, what's the next one? Okay, this is a thought problem. It's kind of a tricky question, but I wanted to drive this point home. The average mass of carbon in naturally occurring carbon, all isotopes together, is 12.011. Assuming you were to pick only one carbon unit, say whether it's an atom or a mole, if it were an atom, it'd be 12.011 atomic mass units. If it were a mole, it would be 12.011 grams for that mole. The question is, if you just pick one, what are the chances of just randomly picking one of those, let's say atoms, with a mass of 12.011? The chances of finding one atom with that value is, there it is, 0. 0 chances, because 12.011 is a weighted average. So you will never find an atom with exactly that value. That's why the answer for 3 is A. Okay, let's do number 4. Let's see, chapter 3, number 4. What's the mass of 4 atoms of copper in grams? This is a dimensional analysis problem. So what are you given? You're given 4 atoms of copper. And the question is, how much is that in grams? Right, so we do equals something in grams. So how do you get from here to here? Do we have one conversion factor that will get you from there to there? The answer is no. If you work backwards from your answer dimensions, then anything related to to atoms, you ought to first consider molar mass. Molar mass will give you grams. So the final conversion factor will be something like this, grams per mole. Right? And we know what that is for copper. Just look it up. Right? This is a problem where you're not given every piece of information you need, but it's available right here. So copper is 63.546. Grams per mole. Okay, now that we've, oops, no, that's right, that's right. Grams needs to be on top. So we got moles here. Do we have a factor that will cancel moles? Right, cancel moles, and is related to atoms. The answer is yes. It starts with an A. It's called Avogadro's number. This cancels atoms, and this mole cancels. And now, once you've analyzed all your dimensions, the only thing you got left is grams, and that's where you need to be. So the rest of it is just crunching numbers. All the thinking is done. So 4 is in the numerator, times 63.546 in the numerator, and then divided by Avogadro's number. And I get 4.22 times 10 to the minus 22 grams. That's how much 4 atoms of copper will weigh. Now, how do we know how many significant figures are here? The sky's the limit. Why? Because conversion factors are always exact numbers. They don't limit your number of significant figures. And your starting point, which normally would limit the number of significant figures, is a counting number. That's also limitless. So you can have just as many decimal places out here as you want, because the problem doesn't restrict you. But I just chose to stop it at 2 decimal places. That's force of habit. And let's see, that's E. This is E. Okay. Whoa. Slide off there. Move it over this way a little bit. Okay. All right. Let's see. I don't want to do any work any redundant problems. How about number 6? This takes some thinking. You're given a sample of zinc and a sample of aluminum. And you have equal numbers of atoms of each. All right? So the number of moles are exactly equal. All right. Which of the following statements concerns the masses of the samples is true? So the masses of this sample and that sample is related some way in these statements. All right. So let's just start at the top. The mass of the zinc sample is more than twice as great as the mass of the aluminum sample. Now, how do you know? Well, you've got to convert moles to grams, right? And you need molar mass. So we did, let's see, zinc is 6539 grams per mole. And aluminum is 26.98 grams per mole. Now, how do you know the grams, the mass here? Well, you don't exactly, but you do know that the number of moles of each is exactly the same. So to compare the two, just pick something. Make it easy on yourself. 1 mole. So 1 mole of this and 1 mole of that would be 65.39 grams of zinc ratioed to 26.98 grams of aluminum. Why did I ratio them? Because A says zinc sample is more than twice as great as the mass of aluminum sample. So when you say twice, you're talking a ratio, something times something else. So the ratio of these two would be what? 65, what's the last? 39. I put a tail on it, shouldn't do that. 65.39 and divide by 26.98. 2.4. 2.4 times. So the zinc sample is 2.4 times as heavy as the aluminum sample. Is that true in statement A? Yes, it's more than twice. So A is true. Now let's look at the rest of them. This is test-taking technique. We've got a statement for each one of B, C, D, and E. There are none of those squirrely ones in there like A and B, or A, B, C and not D, or none of the above, or any of that type of garbage. Each one has a sample, has a statement independent of the others. So that means once you find the right one, you're done. We found the right one, we're done. Okay, let's see. This might be worth working. Number 7. A lot of students get confused with the wording of a problem. A sample of ammonia has a mass of 43.5 grams. Okay, 43.5 grams of ammonia. What's wrong with that statement? Have we ever told you what the formula for ammonia is? You know what ammonium is because it's a polyatomic ion. Ammonia is this one. So in this case, if you get that problem on the test, you have my permission to look it up. What is the formula for ammonia? Just open your book, look it up, and then go on your merry way. Why do we need to know that? Because the question is how many molecules are in this sample. And you can't tell how many molecules there are unless you know the molar mass of the sample. The molar mass of ammonia is what? 14.01 for nitrogen and 3.03 for hydrogen, because each one is 1.01 times 3, 17.04 grams per mole. So now you just have a dimensional analysis problem, conversion factor. So we take this, and we can use this one right side up or upside down, whatever is required. Okay? And in the interest of time, this only tells you how many moles, right? The question says how many molecules, right? So if this is number of moles, how many molecules do you have? Avogadro's numbers. Yep, go ahead.
You just times it by Avogadro's number, right?
Right, right, because it's that many per mole. Right. Cancels the moles, cancels the grams, And this is the number of molecules of ammonia. Now, what if, well, let's see, the answer is 1.54 times 10 to the 24th. Molecules. What if the question had said how many atoms of nitrogen are there? Same number. Because the ratio is for every mole of ammonia, you got 1 mole of nitrogen. So it's the same number of nitrogens as there are molecules. If it says how many hydrogens do you have, then the ratio is different. It's 3 to 1. So it'd be 3 times that would be that many hydrogen atoms for that many molecules. What if it says how many atoms do you have? You know, say I get really sneaky. How many atoms are there? It'd be the number of ammonias plus the number of hydrogens. It'd actually be 4 times that number. Just in case. Okay, that was 7. Okay, I need to pick up the speed here. How about the molar mass? This is number 11. The molar mass of barium sulfite. What do you need to know to answer that question? You need to know the formula. So that's why I was so insistent on you learning how to write names of compounds and how to write compounds from their names. Okay, so what's barium? Right? We know what barium is. It's an alkaline earth. Barium. It's in the second column, so it always has a 2+ charge. Okay. How about sulfite? It's not sulfur, right? So it can't come from here. Sulfite is a polyatomic ion, and you look it up on your table, right? At the very end of the document.
Is it SO3?
Right. And what's its charge?
-2.
Right. Okay. So we've got this species with a 2+ and that species with a 2-, right? Because the 2- is spread over the entire group. You got 1 of each. That's all you need. So our formula is just that. Just those 2. Now we can answer the question. What's the molar mass? So barium's a big atom. It's 137.33 grams per mole. Sulfur's a lot lighter, 3206. Okay. And then 3 oxygens. Just add them together. So the tricky part here was getting that formula right. And add those together and you should get 217.40 grams per mole. And just a word of warning, multiple choice questions, if they're made up correctly, take into account the most common mistakes that the test taker will make. And the problem will be figured with those mistakes incorporated, and that'll be one of your answers. So just because you see your answer there doesn't mean it's right. You have to know that you've done it right to find the correct answer there. Just a word of warning. I don't know what could possibly be 137.33 be 440, 450 something. Well, they didn't do it here. Okay, never mind. Time's precious. Let's move on. How about 17? 17 usually throws my students for a spin. Let's see, 17. A compound is composed of an element, X, and hydrogen. So it's got this in it, and it's got that in it. Okay? Analysis shows the compound to be 80% X by mass. So it's 80% X in that compound. So how much is the hydrogen? 20%, right? Has to add up to 100. So 80% X, 20% hydrogen. Analysis shows with 3 times as many hydrogen atoms as X atoms. Okay, so we're also given this. We're given that ratio. Which element is element X? Okay.
Why don't you just times the hydrogen, the 20% by 3, and then?
Well, yes. This represents 20% of that mass. If we say 3 times 1.03 is 3.03. So 3.03, and then the mass of X, like that, is the total, right? And then 3.03 is equal to 0.20 times the total. I think I'm going about that. I'm making it harder than it needs to be. It should just pop out at me, but it's not doing it. Oh, obviously. Okay. I am making it harder than it needs to be. In order to find out how many moles of each one we have, we need mass. So if 20% is hydrogen, 80% is X, then we just assume, like we were doing our empirical formula, we assume we've got 100 grams. So 20 grams of hydrogen is how many moles? Grams per mole. So we have 20 divided by 1.01. Is 19.8 moles of hydrogen. Okay. So how many moles of X are there? 3 times that many. I mean, a third of that, isn't it? Right? If the ratio is 3 to 1, then 19.8 divided by 3 moles of X. 6.6. And that's all in 100 grams, right? So how many grams of X do we have? 80. And molar mass is mass per mole. So 80 grams divided by 6.6 moles is 12.1 grams per mole. And you know which element that is. Carbon. which in this problem is B. That's what happens when you overthink a problem. It was really simple. What I should have done was start with, where do we need to end up, right? I put what we've given. Where do we need to end up? We need to end up at a molar mass, right? So we need grams and we need moles of X, whatever it happens to be. So how many grams do you have? Well, if you assume that you have 100 gram total, then you have 80 grams of that sample. And if you assume 100 grams, then you have 20 grams of hydrogen. And 20 grams of hydrogen can be converted to moles, which we did. And then the ratio of moles to moles is 3 to 1, which gives us moles here. So I was working from the wrong end. Actually, this problem works better if you go to the tail end and work your way backwards. Okay, we need to move along because we've got 2 chapters to cover today. I'm going to skip that one. Okay, this shouldn't take too much time. Number 32. And we're still in chapter 3. The empirical formula for styrene is CH. Okay. And its molar mass is 104.1 grams per mole. So the molecular weight is that. So how do you get from there to answer the question, what's the molecular formula for styrene? Remember, we need, if this is the empirical, we need some value here that multiplies by every subscript in the formula to give us the molecular formula. The empirical formula is the simplest whole number ratio, which is 1 to 1. So the easiest way to do it is calculate what I call the empirical formula. The empirical mass, pardon me. So the empirical mass of this, if X is 1, is 12.01 and 1.01, which is 13.02 grams per mole of formula. Okay? And then you ratio this one to that one to find out what X is. Okay? So this one divided by this one is what? It's probably, it's like it's in the neighborhood of 8. $7.995. Okay, so that's your X. That means the formula is C8H8. Okay? Rather than take percent by mass composition and work a whole problem like that, this focuses on what you do when you've got to this step and you need to go to the next step. Go to the next step. Okay, let's see. I think we did this one in class, adipic acid. What's the empirical formula? Let's see if we can find another one instead of doing that one over again. Maybe we can't find another one. Or maybe I can't find another one. Doesn't mean it's not here. Okay. Didn't we do this one in class? Adipic acid? Let's do this one. 74. All right. So our end game here is finding the empirical formula for epinephrine. What's another name for epinephrine? We got any anatomy students in here?
Is that adrenaline?
That's exactly the same thing. Adrenaline and epinephrine are the same. Yep. Okay, so we're given a lot of blue smoke in this problem. The first two sentences, first two sentences are, well, 75% irrelevant. It does tell you that it's composed of carbon, hydrogen, oxygen, nitrogen, and that's it. And then it gives you percentage composition values. So it asks, what's the empirical formula? All right, so we're given this. I'm gonna squeeze it way over here. Yeah, still see that. 59%. And hydrogen is 7.15%. Oxygen is 26.2%. And nitrogen is 7.65%. By mass. So what's the first step? We can't find out what the mole ratio of these elements in the compound is because we don't have moles. All we've got is percent, and percent is even a dimensionless number. But it does tell us that if we know that it's percent by mass, then it's 59 grams per 100 gram sample. So if we assume a 100 gram sample, then we have a mass to work with. So in the interest of space, assume 100 grams, and then that goes away and we replace it with grams. Okay, now we got something we can work with. And call on Henry Ford. Set up assembly line. We need to convert to moles and cancel grams. So grams has to be in the denominator so that moles can be on top. Okay, so carbon, 12.01 per mole. Hydrogen, 1.01 per mole. Oxygen, 16 per mole. And nitrogen, 14.01. Okay? Now let's do a little calculation. 59 divided by 1201 is 4.91 moles. And 7.15, 1.01 is 708 of hydrogen. Oxygen, 0.2, 16, is 1.64. Okay, and nitrogen is 7.65. And 14.1 is 0.546. Okay. Now, next step. This is the ratio of moles of each of the elements in the compound. But they're not whole number ratios. And to get the empirical formula, we need the simplest whole number ratio. So the first thing we do is just take the smallest one and divide everything through by that one. So we divide everything through by 5, 4, 6. Right? That means divide the whole stack. That one's going to be 1. 1.64.546. This one is 3. Now we're rounding off, especially if it's very close to a whole number. 708 divided by 0.546 is rounded off to 13. And carbon, 0.546 divided into that is 9. Okay? Now, can we simplify this any further? Well, chances are you can't, because this one's already 1. You can't make it any smaller, and you don't want to go up. So what we have is carbon is 9, hydrogen is 13, oxygen is 3, nitrogen is 1. So that's the empirical formula for epinephrine. Of course, usually, though, we write nitrogen in front of oxygen. But that'll get you all the points in the problem. Okay. So now, let's see, I skipped a bunch. Let me go back to I want to get on chapter 4 pretty soon. So we're going to look at number 45 and number 60. And number 60. Because they both use similar types of diagrams. Okay, for 45, if we have a chemical equation with this hypothetical, the question is, which one of these figures, a Roman numeral 1, 2, 3, or 4, best approximates the stoichiometric ratio of A and B? Okay, we can go process of elimination here. If we're only looking for the stoichiometric ratio of A and B, that means anything that's got C in it is out, which means Roman numeral 4 is gone. You can't use it because the question asks for A and B only. So now you look at 1, 2, and 3, and you say, all right, what's the ratio? Well, for every 2 A's, there's 1 B. So you just add them up. Roman numeral 1, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 A's and 4 B's. So Roman numeral 1 satisfies. How about 2? Let's see, A's, we got 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8 B's. Wrong ratio, that's 1 to 1. How about Roman numeral 3? 1, 2, 3, 4 A's and 8 B's. That's flip-flop, that's the wrong direction. So Roman numeral 1 is the only one that works. That's A. Okay, now let's turn to 60. And it uses a similar, not exactly the same, but similar. And we're asked a chemical reaction has an equation here, same chemical equation, in which case is B the limiting reactant. All right, so what does that mean? If B is the limiting reactant, that means A must be in excess. So if the ratio is 2 A's for every B, if you get a ratio that's in excess of 2 to 1, then that one satisfies because A is excess and B is limiting. All right, so let's look at it. Roman numeral 1. 1, 2, 3, 4, 5, 6 A's. So we have 6 A's and 1, 2, 3, 4, 5, 6 B's. That's 1 to 1. Can't be. It's got to be 2 It's got to be greater than 2 to 1. So Roman numeral 1's out. How about 2? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 A's, and 1, 2, 3, 4, 5 B's. So 2 to 1 would be 10 to 5. This one is excess A. Roman numeral 2 satisfies. Let's see about 3. 1, 2, 3, 4, 5, 6 A's, and 1, 2, 3, 4 B's. Right. That's less than 2 to 1. 2 to 1 would be 8 to 4. So Roman numeral 3 can't work. How about 4? 1, 2, 3, 4, 5, 6 A's, and 1, 2, 3 B's. That's stoichiometric, exactly 2 to 1. That doesn't work either. So Roman numeral 2, which is B, answer 60. Okay? Does that give anybody trouble? Okay. So let's see, did I skip anything important? No, we're going to move on to all right, we'll pause temporarily for 64. So 64 addresses the calculation of percent yield. Right? So percent yield we found was what? The mass of actual product divided by the mass of theoretical product times 100. Okay? So now we're going to turn that around and say for this reaction, the percent yield for this reaction is 82%. So what does that mean? There's only one product, right? So the percent yield of hydrazine, N2H4, is 82%. 82% equals mass, let's see, actual divided by mass theoretical of hydrazine times 100. Okay. What's the actual mass of hydrogen produced when 25.57 grams of, oh, this is going to take a while. Okay, 25.57 grams of nitrogen is reacted with 4.45 grams of hydrogen. All right. And the question, let's look at the question again. What is the actual mass? I want this one right here. So in order to satisfy that, we've got to find out what the theoretical is. So the theoretical would be reacting this with this to give that. Okay? So this, since you're given exact amounts of this one and that one, you should always suspect one of us is limiting. So I'm already into it. We might as well do it. Okay. We'll leave that there as long as we can. So how do we find out which one's limiting? You can't go anywhere in these problems unless you have moles, correct? So we got to find out moles of nitrogen. So what's the molar mass of N2? It's 2 times 14.01 or 28.02. So 25.57 grams divided into is 0.916, 0.916, 9126, excuse me, moles of nitrogen. Okay, I'm gonna have to erase this. Sorry. Hydrogen. Got to convert it to moles. So with diatomic hydrogen, we have 2.02 grams per mole. So 4.45 and 2.02 divided into it is 2.203. 203 moles of hydrogen. Now, how do we tell which one's limiting? You say, if all of this is converted to hydrazine, how much do you get? And if all of this is converted to hydrazine, how much do you get? And the one that makes the least amount is the limiting reactant, and the one that actually produces the theoretical amount of hydrazine. So we got to do a conversion here. So we got to cancel nitrogens and leave us with hydrazines. So the ratio is 1 to 1, right? So that's how much hydrazine you have. How about hydrogen? Well, one of these and two of those. So hydrazine is half of this one, 1.115 moles of hydrazine. All right, so which one's limiting? Nitrogen is limiting. That means we only end up with 0.9126 moles of hydrazine. And this has to be converted to grams in order to find out what's the theoretical mass of hydrazine. So we got to cancel moles, leave us with grams. So what's the molar mass of hydrazine? Well, 2 times 14.01 is 2802. And 4 hydrogens is 4.04. So 3206 is the molar mass of hydrazine times, oh, I don't have it there, 0.9126 times. So this is 29.26 grams, theoretical. Okay, now we can go back to what's our percent yield? 82% yield, which means that 82% of that is the actual amount that we end up with. 29.26 grams. And what's the fractional equivalent of 82% is 0.82. Which is 24.00. And looks like it's B. Okay? That was longer than I expected. I didn't see that one coming. But it did give us some exercise in limiting reactants, so it's not a total waste. Let me see. Let me check my schedule because I'm going to follow my pattern, and I'm just going to keep talking until I'm finished. And I want to be sure I don't have something else waiting in the wings that I'm responsible to be doing. Other than the fact that I've got office hours. But I'll sacrifice some office hours to get this done. Okay. So that was number 64. Let's see. '72 would be interesting, but we don't have time. I think it's more important to look at 73. Because I found my students, sometimes they don't visualize things very well. 73. So with A, we have a representation of a molecule that has so many carbons in it and so many hydrogens in it. What does the question ask? The question asks the empirical formula. The empirical formula is the simplest whole number ratio. So if you count up those carbons and hydrogens and say C6H6, yeah, that's wrong. That's only an intermediate step. The final step is reduce it to that. That's the empirical formula. And we can go right on down the line. The next one is molecular formula, and this is empirical formula. So this one's that. That means this one is the same as that one. Oh, wait a minute, I got it wrong. Nobody caught me until I caught myself. There you go. I miscounted. 2 carbons and 4 hydrogens makes CH2. This one looks like it has carbon, hydrogen, and oxygen. So how many carbons? 1, 2, 3, 4, 5, 6. Hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And oxygens. 1, 2, 3, 4, 5, 6. It looks like glucose to me. So what's the empirical formula for glucose? CH2O. Why? Because you can divide this through by 6. 6 into that, 6 into that, 6 into that gives you 1, 2, 1. And D, looks like carbon, hydrogen, and oxygen. All right. Carbon, 1, 2, 3, 4, 5, 6. Hydrogen, 2, 4, 6, 8, 10. And oxygen, 2. So the least common denominator here is 2. So that means C3H5O. All right, that's 73. Let's see, we did 74 already. Now we're ready for chapter 4. Chapter 4. All right. The first questions in this bunch are just, you got to memorize it. You got to know at a glance. For instance, number 6, which of the following is paired incorrectly? right? A through E. Strong acids, strong bases, weak bases paired with molecules. A, H2SO4, what is that? Sulfuric acid. Strong, that's correct. HNO3, nitric acid. Nitric acid is a strong acid. Oh, weak acid, they called it wrong. B is paired incorrectly. Well, test taking technique. The rest of them that have nothing to do with the ones above them. So you find the right one, you're done. Because it only asks for one. Which of the following is paired incorrectly? Barium hydroxide is a strong base because it's an alkaline earth hydroxyl. HCl, hydrochloric acid, is a strong acid. NH3, there's your ammonia. Ammonia is a weak base, right? If we didn't cover that in class, I'm telling you now, this is a weak base. Why? Because when you put it in water, what does it do? Right? Ammonia is a gas. When you bubble it in water, bubble it through water, dissolve it in water, it reacts with the water. And produces that. It doesn't stay like that. Oops. Plus 4. There. That makes it a base. Well, what's the equilibrium? That's the question. If it's a strong base, it would go here, all the way over here. Everything's down here. But it doesn't do that. In fact, I've done some calculations, and I think I've got a document on it. I don't know if I posted it or not. But for now, take my word. This solution, this in solution, in fact, this will go into solution and become dissolved in the water. It's not a gas anymore. And this equilibrium is 98+% ammonia. That means it's a weak base. All right. Okay. I got this one circled. Let's see. All right. Solutions. So if you have, this is 12. How many grams of sodium chloride are contained in 350 milliliters of 0.287 molar solution of sodium chloride? So what is that? Let's see, what are we given? 350 milliliters. That's volume of 0.287 molar. So the molarity is 0.287 molar. And the question is, what's the mass of sodium chloride in that solution? Can we calculate it directly from that? No, because the definition of molarity is moles per liter. Right? So remember, molarity equals moles per unit volume. If we want to find out how many moles there are, which is on the way to finding the mass, we need molarity times volume. So this times this will give us the moles of sodium chloride. .10045. 0.10045 moles. Okay? So now it's simple, right? If you need mass and you've got moles, you need molar mass for the conversion. So 0.10045 moles converted to mass, we need a molar mass for sodium chloride, which is, sodium is 23 and chloride is 3545. If you don't believe me, look it up. It's right there on the chart. 5845. All right, times, let's see if I still got it in here. Yeah, there it is. 5.87 grams. Okay, and the nearest one to that one in our choices is B. Wait a minute, that's not, I'm looking at the wrong one, sorry. Is, yeah, is B, 5.87. Okay, that was a really simple problem just to get our, to wet our palate. Okay, so here's a better one. Suppose you're working in a lab. Some of you might have that ambition. And you need to prepare a solution that's a particular molarity in a given compound. In this case, we need 1.49 molar calcium chloride. Okay? Now, if that's all you're given, then you can choose the volume and make it up however you want. But this problem says you need 3.950 liters. Okay? And the question is, what mass of calcium chloride do you need to weigh out in order to make that volume? This is the volume of the solution. Right? So how do we know? Well, we got to find out how many moles first. Right? This volume times that molarity equals what? Equals 5.886 moles. Now we can convert grams. Now we can convert these moles to grams, and that's how much we weigh out to dissolve in this many liters. Final volume. So calcium chloride is, let's see, 40.08 for calcium. And 2 times chlorine, 3545. Oops, wrong. Try that again. 3545. 2 times. So we have 110.98. 110.98 grams per mole. Times 5.86 is 65.65. Let's see, only 3 significant figures, so we have 65.3 grams. Let's see where that, which one is that? No, I read it wrong. 653 grams. Right, 653 grams. E. Okay. So let's move on. Time's up. Oh, a bunch of people still here. That's encouraging. The next one is a dilution problem, number 18. Okay. So let's say you have an 18 molar sulfuric acid, 18 molar H2SO4 aqueous. 18 molar. That's pretty concentrated. It's not as concentrated as you can get. 98% sulfuric acid is 36 molar. So that's about half strength of what you can buy from a supplier. But you've got this 18 molar sulfuric acid, and let's see, where was I? And you need to prepare 2.3 liters of 0.145 molar. 0.145 molar sulfuric acid. You need, how much of this, how much of that do you need to dilute to this volume to give you that concentration? And remember, concentrated, dilute, okay? That's our ratio. So the concentrated here, this is the 18 molar. This is the volume that you need to bring out. This is the volume you dilute it to. So pause for a second. Look at the answers. The answers are in milliliters, right? So let's save ourselves a step. Instead of putting 2.30 liters in this volume, let's make it milliliters, so our answer will come out in milliliters, right? So how many milliliters is 2.3 liters, right? 2,300, right? Move the decimal place 3 to the right. And then solve for this one. So you just multiply that times that, divide by this, and you got your volume. And it should be 19 milliliters. 19 milliliters of that solution diluted to this volume will give you that concentration. All right? That was 18, which is A. Okay, still got some people hanging in there. All right, the next series of questions, 26 through 29, are there for you to identify what types of reactions we have here, recognizing reactions. All right, so 26, and remember, the classifications that we use for our reactions can apply multiply. That is, one reaction can be more than one type of reaction. Okay. So don't lose track of that. And in fact, no, I don't see any like that. I think I corrected that mistake, which is neither here nor there. But these are your 3 reactions. This one, and this. Okay, this one yields that plus this. And the last one. What does that mean? That's an abbreviation for acetic acid. Here's your acidic proton right there. And this is what's left over. Ammonia is this and this. Okay, so the answers we have to choose from are in order. This one, then that one, then that one. So respectively, what type is this one? This should pop out as a net ionic equation. because these are not necessarily counter ions in solution. But if we look at that, lead iodide, is that soluble in water? Right? These are all aqueous reactions. Is that soluble in water, or does it drop out? Is it a precipitate? Well, as written, we would assume that it's a solid, because it's not, it doesn't say it's aqueous. Of course, these have to be aqueous, right? Or they won't be individual ions. To confirm, you just look at your solubility chart, follow the lead over to the lead on top and go down, I think. Anions on the side. Yeah, anions on the left-hand side. Follow it down to iodide, and you'll find that that is insoluble. So this is a precipitation reaction. How about this one? Notice that you've got a change in the oxidation state, 4+ to 3+. And this one goes from an ion to an element. And this is kind of a corollary to one of the tricks I gave you. If it starts off in a compound, ends up as an element, that's an oxidation reduction. But you can also tell by the change in oxidation state, that's oxidation reduction, definitely. This one, that's an acid. This is a base, right? Right, so it's acid-base reaction. This is your acid, there's your conjugate base. This is a base, there's your conjugate acid. All right, that's 26. Let's see if 27 can give us anything new to learn. Nah, 27 is kind of a rehash. 28. That's a rehash also. You'll notice that both of those reactions in 28 start off with solutions on the reactant side and end up with a solid on the product side. That is a precipitation. In fact, both of them are precipitation reactions. How about well, 29, there's one giveaway here. All of these reactions are a certain type. So if you identify the type of one of them accurately, well, no, you better look at all of them. Scratch that. Better make sure that they're all the same type of reaction. So the first one, aluminum and bromine, yields a compound. Right? That is an oxidation reduction because you have elements on one side, compound on the other. But could it be something else? Well, if you have two elements on the reactant side and a compound on the other side, that is a my mind's gone blank. Synthesis. That's a synthesis reaction. But is synthesis a choice? No, synthesis is not a choice in this one. And it's a good thing because the next one is a decomposition. Right? Silver oxide yields silver and oxygen, compound to elements, oxidation reduction. And the last one is a combustion reaction. Right? And all combustion reactions are oxidation reductions. Why? Well, oxygen is a reactant on one side and it's in a compound on the other. Right? That's a giveaway. But it's also a combustion reaction because anything that combines with oxygen to yield products with oxygen as part of their makeup is a combustion reaction. We could even do this. Right? That's a combustion reaction. That's iron burning. Okay? You didn't know iron would burn, did you? Well, it's also rusting. Depends on the speed of the reaction. Okay. So let's move on to, let's see. This is sort of a detective. Number 30. Oh, we're down to 1, 2, 3, 4, 5 people left. This is number 30. This is a detective story. You have electrodes in a solution of sulfuric acid. Okay? Electrodes attached to a battery and a light. And when you put your electrodes in the sulfuric acid, of course, the light bulb is bright because this is a strong acid and it produces ions in solution that can transmit the charge from one electrode to another. Right? So you have a circuit. Right? So that's our established condition at the beginning. Now the question is, you add a dilute solution and the bulb gets dimmer. So if this is happening in solution, right, and these are aqueous, that's why the electricity is conducted through the solution. Then if the bulb gets dimmer, what are we doing? We're removing ions from solution, right? That means precipitation. We've added something to the solution that combines with one of these to remove them from solution. I don't know of any compound that has hydrogen as an acidic component that is insoluble. So it has to be the sulfate. Something's combining with the sulfate. So which of the following could it be? Well, we need to combine sulfate with something that makes a solid. And this could be almost anything. It could be multiples. But we need something, a metal, has two conditions. The solution that we add to this, it must be a solution. Whatever you've got in there has to be soluble. And then the other condition is that the cation of that solution must form with an insoluble compound with sulfate. So let's look at that one first. Let's go down the list. So what are the cations that we have available? And E is none. Okay. So the first one is barium hydroxide. Right? Second one is sodium nitrate. Third one is potassium sulfate. And the fourth one is copper 2 nitrate. Okay, let's look at these. How about barium and sulfate? If you look up barium sulfate in your chart, you'll find that it's insoluble. So barium sulfate is a candidate. That may very well be the one. Let's look at these others. Sodium sulfate, soluble. All sodium salts are soluble. Potassium, all alkali salts are soluble. Copper sulfate. Look it up in your chart. Copper sulfate is soluble too. Okay, so that takes care of the solubility problem. How about, is this an aqueous solution, right? Because it has to be in solution in order to react. And the conditions of the problem say a dilute solution was added, right? So what's the solubility of barium hydroxide? Well, let's look at our chart. There's barium, there's hydroxide. It is soluble. Barium hydroxide is soluble in water. So there's your answer. Okay. Oh, okay, let's do this one. Number 38, 39, and 40. They're all based upon the same reaction chemistry, just different questions. And in order to answer the question, each of those questions, you have to perform the reaction. So this is 38 through 40. So the balanced molecular equation contains which of the following terms? That's 38. The balanced complete ionic equation, which of the following terms? And 40, the net ionic equation. So that's why they're put here together, because the same reaction, molecular equation, or formula equation is probably more accurate. Complete ionic equation, net ionic equation. So we got to do all three of them to answer those three questions. So we might as well do that first, then we can answer. So we're reacting barium chloride. Barium is a 2+ cation from the second column. Chloride is a halogen -1, so that means we need 2 of those. And all chlorides are soluble. Almost all chlorides are soluble. In this case, yes, it's soluble. Plus, you're told that it is. Solutions of barium chloride and silver nitrate. Okay, so what do we get from these? Remember the double replacement? If we're going to do a molecular equation, we swap these 2 cations. Cations. So silver comes over here to chloride. Silver's 1+, chloride's 1-. And is it soluble? No. Silver chloride is insoluble. And then barium and nitrate. How about that one? Look it up. It's soluble. In fact, all nitrates are soluble. Okay, so there we have, first condition is write your compounds correctly for the reactants. Then the question is, how does the reaction proceed? When these aqueous solutions are added together, you just do a double replacement. You say this one substitutes for that one, and that one comes over here. What do you get? You get this one plus that one, there. This one plus that one, there. Right? And then you say, are any of them insoluble? Right? And then you identify them. Now you balance the equation. 1 barium, 1 barium. Instead of setting up a budget, this should be fairly easy. 2 chlorines, 2 chlorines. That gives us 2 silvers. 2 silvers. We didn't write this one correctly, did we? 2+, 1-. So let's check it again. 1 barium, 2 chlorines, 2 silvers, 2 nitrates. Now we have a balanced molecular equation. At this point, we can answer 38. The balanced molecular equation contains which of the following terms? The only one that fits out of that whole group with its coefficient as a term is this one. That's B. The second one is balanced complete ionic equation. So how do you do the complete ionic equation? This is a 2+ in solution. This one is a 1-, and you have 2 of them. This one is 1 plus, and you have 2 of them. And this one is 2 of these. And then I'm going to draw this over here. And then on the product side, you have that remains whole. That precipitate cannot be broken apart. So you have to leave it alone. But this one can be. It's in solution. You have 1 barium plus 2 nitrates. That's your complete ionic equation. And we can answer 39 now. The balanced complete ionic equation contains which of the following terms? The only one that fits there is that one. The rest of them are all wrong because you have to consider the coefficient as well. Right? They're giving you coefficients at the same time. That's why it says which of the following terms. That's a term, that's a term, that's a term. Okay, so that was this one for 39. Now for 40, we need the net ionic equation. So how do we get the net ionic equation? You look for duplicated terms on both sides and cancel them out. Barium, barium. Reactant side, product side. Chloride, nope, can't get rid of that one. Silver, nope, got to keep it. Nitrate. That's it. Now, the net ionic equation is, we usually write the cation first, so I'm going to put this one over here. So what's wrong with this picture? You've got 2, 2, and 2. That's not the simplest whole number ratio, is it? So that means that becomes 1, 1, and 1. That's the trick in this question. The net ionic equation contains which of the following terms? This one. Okay? And of course, test-taking technique, when you look at the answers, none of them has a 2 in front of it. So you go looking at your problem and say, oh yeah, simplest whole number ratio. All right. So I'm 20 minutes over the end and still steamrolling. Let's see. How many more? We got a few more. We might get done by 2:30. Let's see. Do we need to use this one? Yeah, it might take us a while, but this is worth doing. Okay, 46. All right, if all of the chloride in a 3.734 gram sample of an unknown metal chloride is precipitated as silver chloride, and we do that using 70.9 milliliters of a 0.201 molar silver nitrate solution, what's the percentage of chloride in the sample? All right, let's see, what are we given? Now let's write the equation first, right? The reaction. What reaction do we have? Well, we have a metal chloride. We don't know what the ratio is here, but it may not matter. So let's keep going. We're going to react that with silver nitrate solution. And produce silver chloride, solid, plus the metal nitrate. And we know that's in solution because all nitrates are soluble. Okay, now recognizing that this is not necessarily balanced because we don't know what the ratio is here, right? So we can't balance the equation. But this gives us a bird's eye view of what's going on in that precipitation reaction. And all of this is converted to that. Every bit of that is converted. Okay, now what are we given? 3.734 gram sample. 3.734 grams of that sample. Right there. And it's precipitated with 70.9 milliliters. 70.9 milliliters of a solution that's that molarity. And the question is, what's the percentage of chloride in the sample? So the question is, percent chloride in that sample. All right, this is everything that we're given. We may have to look some other stuff up later, but for now, what do we need to do to calculate this? Right here. We need to know the mass of chloride in that sample so that we can ratio it with this value. So the mass of that divided by this times 100 is this value. So we're looking for the mass of chloride. So how do we find the mass of chloride? Well, we have to look for the other side. If all of this is converted, then all of the chloride now is over here. So how do we know how much of that is? Because we know that this is stoichiometric with that. So if we find out how much of this it is required, we can do a mole ratio from here to here. Right? So how many moles do we have here? That times that. All right, I'm going to throw you a curve. I multiply milliliters times molarity. Right? Normally, that would be forbidden because it won't give you moles. But it does give you millimoles. Now, the reason I'm doing this is because I want you to know that when you get out there, somebody throws this term at you, you won't be completely surprised. Millimoles is just milliliters times molarity. And if you want to convince yourself that this is true, you say, if this is millimoles, how is that related to moles? Well, this is 1,000th of a mole, right? So we got to move it 1, 2, 3 to the left. 0.01425 moles. Right? Equals that many millimoles, right? So if we say this is how many liters, 0.0709 times 0.2, you get that value, right? So I'm not lying to you. Millimoles, okay? If the ratio is 1 to 1 here, we know that ratio is true. So we should have this many millimoles of that solid. Okay? But of course, we need to know how many moles, right, to use molar mass. So I sort of shot myself in the foot here. So how many moles of this do we have? 0.01425 moles. That's moles of silver chloride. How many moles of chlorine do we have? Same thing. Right? We have the same moles of chlorine here as we do silver chloride. So now we've got moles of chlorine We know that all of this chlorine came from that source. So if we convert this to mass, we can do this calculation. So we'll say this is moles. We need to convert moles to grams, 35.45. I haven't memorized because I use it so much. So how many grams is that? Because moles cancel. So let's see, 1,000, convert this. There we go. Now, 35.45 times is 0.5052 grams. All right, now we can do our calculation. 0.5052 grams of chloride in 3.734 grams of XCl times 100. Is 13.5. Let's see. 4 significant figures, 13.53. Now, what comes close to that? Exactly, B. There you go. So that's kind of a detective story also. Oh, before I forget to mention it, the exam has 39 points required. So that's the denominator. Whatever points you get on top, divided by 39 times 100. This one, for some reason, I have loaded it massively with bonus. 27 points of bonus. All right? So you could really clean up on this exam and put in a lot of buffer for later in the semester. And remember, the bonuses don't cost you anything. If you've got the time and energy, work all the bonuses and squeeze as many points out of this thing as possible. Let's see. All right, this one shouldn't take too long. Number 47. You have 88.6 milliliters of 2.5 molar sodium chromate. Solution. And 125 milliliters of 2.5 molar silver nitrate. Okay, so this is 88.6 milliliters of 2.5 molar, and this one is 125 milliliters of 2.5 molar. What's the concentration of sodium after the two solutions are mixed? So what do you get? You get sodium nitrate. Oops. Sodium nitrate, which is soluble. All nitrates are soluble. And silver chromate. Look it up. Silver chromate. Let's see. This is 2 of these. Is a solid. Okay? Now, in the interest of saving time in a stressful environment, namely exams, do we need to balance this thing? What's the question? The question is, what's the sodium concentration in that solution at the end? Here's what you do. You say, all right, visualize all the ions in solution. So on this side, you have sodium ions, chromate ions, silver ions, and nitrate ions. What do you have on the other side? Sodium ions, nitrate ions, silver chromate solid. Sodium ions are on both sides. It's a spectator. You've got the same number of sodium ions on this side as that side. So the calculation is fairly simple. How many sodium ions do you have? Right? Well, in this case, we're going to use millimoles again. 88.6 times 2.5 is 22.15. 22.15 millimoles. Right? What's the concentration on this side? Well, it's moles per liter, right? But here's another thing. Millimoles per milliliter is equal to molarity, which is equal to moles per liter. Why? Because the milli cancels out. If you cancel out the milli, you got moles per liter. So this calculation gives you exactly the same value that the molarity that you would have for sodium. So this is the amount of sodium. What's the volume? The volume is 88.6 plus 125. Or 213.6. 213.6 milliliters. So you divide this one by that one because of this, and you get molarity. 1.0, let's see, how many? Three significant figures, 1.04. Right? All because sodium is a spectator. And let's see, where am I? Wait a minute. What did I do wrong? I didn't take into account, this is the molarity of sodium chromate. What's the molarity of sodium ions? Twice that. Okay, so that's C. And this is one of those problems that has the wrong answer in it. So if I were in a hurry, I would have picked the wrong answer. Pick B, it's wrong. Pick C, it's right. Because you have to take into account this source gives you twice as many sodium ions as moles of the compound. This is molarity of the compound. Molarity of the sodium is twice that. Okay. All right. Okay. When I come back, we're going to do 49. I'm going to be gone for 3 minutes. I'll be right back.
If any of y'all figured out how to throw subscripts in on a PDF,
Hey, no, I haven't.
okay, I was just wondering. I've just been struggling to figure out how to do a subscript with it. I mean, I was able to go through like Microsoft Office. I
Yeah,
was able
that's
to
what
go through like Microsoft Office and then type it in and then try to put it back in PDF. But I
I
mean,
did. I
it seems
copied and
like,
pasted it.
yeah, it just feels like a lot of unnecessary work.
Yeah, but that's exactly what I did because I was like, well, I don't know how to do this any other way. So,
Well, he told me to get like Acrobat Reader DC,
uh,
and I just downloaded it, and I'm still having a problem with it. So I don't know.
yeah.
I heard that.
Yeah.
So, so what kind of problem is it not saving your work?
No, I just pulled it up and I threw the exam up on there,
Uh-huh.
and like I'm able to put in the fillables, but I still can't get the subscript to work.
Oh,
And I'm
okay,
using Adobe Acrobat Reader DC.
Yeah, I've
okay.
had the same issue.
I'll if you put your subscripts in the right place, I'll read them as subscripts, right? Because I'll give you credit for it.
Okay, I was just wondering because
Yeah.
I was really struggling, and then like I tried a different one, and it would just like it would let me like it would let you go into subscript and prescript, but it wouldn't like apply it on there for some reason.
Okay.
I just went to Microsoft Word in my last test and typed it in there and then like copied and pasted.
That's what I had to do last time as well, and I just feel like that's a lot of unnecessary work when it's
Yeah.
there was a way where I could just type it in.
There's I can think of possible problem where you have ions, where you have like SO4 2 minus. If you don't have subscript superscripts, it's going to look like this. It's just going to look like that. So if you put the subscript first and the charge second, then that'll be our standard format. Okay, then you won't have to do superscript subscript.
Okay.
Some of my students do it like this. Let's see. Now, how would you do subscript? They don't have a down caret. Oh, never mind.
I mean, I guess you could like draw it on there, but I mean that'd look kind of messy.
Yeah, that would work. You could use the drawing tool and do it by hand. I'm just now trying to get used to using this drawing pad, but I'm not very good at it. This thing right here. It's really jerky, so it's not any better than using the mouse.
Yeah.
Okay. Yeah. Any other problems, questions? There are a few more things I want to cover because I think they're important. And one is number 49. And the reason I want to stop at 49 is one of your labs requires you to calculate the molar mass of an acid by titration. And this is a direct application of that method, number 49. So I thought this would give you some an exercise in how to do that calculation. Okay, so what do we got? An unknown diprotic acid. So a diprotic acid is going to be like this. and then something following it requires, and is titrated with sodium hydroxide. And these are both aqueous. So we're titrating it with that, and we're given 44.39 milliliters of 0.111 molar sodium hydroxide. We do know the mass of the sample, 0.580 grams. That's important because you can't calculate molar mass if you don't know both the moles and the mass. So we've got the mass already. That's good. All right, molecular weight is going to be mass divided by the number of moles, whatever we determine. We get the moles from this reaction. So we've got this one titrated with the acid, and it's exactly this amount, stoichiometric with that amount. So what do we got on this side? Well, we have sodium and X, and that's still in solution because all sodium salts are soluble. And then we have water. Right? All acid-base reactions produce a salt and water. This is the salt, there's the water. So what's the ratio? Well, we have two of these, and we have one of those. But if we're going to have two over here, we need, what that tells you is this is a 2- charge. Right? So that means you need two of these. And you need two of those, and you need two of those. Now, did I do that too fast? Hydrogens are always +1. So the X we know has to be a 2- charge, which means that with this one a 1+ and this one a 2-, you need two of those. Now that we have that, the rest of it can be balanced. We need two of those here, which means 2 hydrogens, 4 hydrogens, and 2 oxygens. 4 hydrogens and 2 oxygens. Balancing this equation is absolutely essential. Even though we don't know what X is, we do know what its charge is. Okay, now, how much of this are we starting with? Well, let's change that to liters. There. Times this, that'll give us moles, because we're eventually going to have moles anyway. So let's just go ahead and dispense with the millimoles and use moles. 0.04439. So that times that gives us this many moles. Of sodium hydroxide. Okay? Now, the only reason we needed to know this side of it was to get balanced for this side, because we're going to convert this to that in moles. Right? So now that we have this many moles of that, how many moles of this do we have? Well, the ratio is 2 to 1. Right? For every 2 of these, we have 1 of those, so we need half of this. And if you were to use dimensional analysis, it would look like this. Right? So we'd have 2 of these, 1 of those, divide 2 into this. And we actually have 2.464 times 10 to the minus 3 moles of H2X. Almost there. We got mass, we got moles. So we take this one here, put it in there, divide this into that. And I get 235, let's see, three significant figures, 235. Okay, let's see, 49. That's B. So that's the type of calculation you'll be doing in that lab. Now, we do know what this is in the lab. When we titrate it with sodium hydroxide, we titrate citric acid. And citric acid, we know, is triprotic. So it's going to have a 3 here to do your calculations. And we also, I think you're also given the formula for citric acid so that you can do a theoretical and compare it with the actual that you obtain and see what your error is. But I'll go through that in a little more detail when I produce the video for that lab. I haven't done that one yet. Probably do it this Friday. But it's on down the road, so there's no big hurry. Okay, that was 49. Oxidation states. Are you comfortable with calculating oxidation states? You have to know the rules, right? Because oxidation state calculations are a way of bookkeeping. It's not necessarily a physical reality. We're just trying to keep track of electrons so that we can to write a reasonable oxidation reduction reaction equation. So we need to know, in this case, say 52. We're given these compounds. Oops. And this one, and this one, and this one, and this one. Okay, and the question is, what's the oxidation state for nitrogen? Because well, actually, the question is, which one has a +4 oxidation state? All right, so you got to do all of them. Or you can start at the top, and then when you find the right one, stop, because they're not related in any way. Okay, so how do we do the oxidation state? Well, for all compounds, the sum of all the oxidation states in your molecule must be 0. For ions, the oxidation states have to add up to the charge of the ion. So these are all compounds. We can just use the first one. They all have to add to 0. Hydrogens are +1. Oxygens are -2. Chlorines, halogens are usually -1. Fluorine always -1. And the other halogens, -1 if you have to choose. So for the instance, this one is going to be -1. The rest of them, oxygens -2, -2, -2, -2. There's hydrogen +1, +1. And sodium is the charge on the cation, which is +1, right? So now that we know all those others, oxidation states, we can calculate nitrogen. Okay, so what do we have here? We have 3 times 2- is 6-, or yeah, 6 minuses, and then we have 1+, right? So that's a 5-. That means nitrogen has to balance 5 minuses with one atom, which makes it 5+ oxidation state. Okay. So that's not the one. This one is NO2. 2- times 2 is 4-, and nitrogen has to balance all of those with 1, so it's a 4+. That's our answer. But for giggles, let's just go and do the rest of them. This is 2-. It has to be balanced with 2 nitrogens at 2+, And each one of these nitrogens then has to be 1 plus. Chlorine is -1. 4 pluses from hydrogen, and a -1 is 3 pluses. So this nitrogen is 3 minus. Okay. If you look at your periodic table at the nitrogen in the right-hand side of that little box, it's completely filled with oxidation states. It can be almost anything. This one is a +1, and 3 times 2 minus is a 6 minus, and a +1 is a 5 minus. That means this nitrogen is a 5 plus. Notice that this nitrate is a polyatomic ion, and that nitrate's a polyatomic ion. So this 5 plus and that 5 plus make perfect sense. It's the same polyatomic ion, so the nitrogen should be the same oxidation state. But the rest of them are variable. And we found our answer at B. Okay, let's see. Yeah, we've already done 60. Balance the following equation. Number 77. Let me see. Well, number 77, does anybody know what that looks like? That's nitroglycerin. So when nitroglycerin decomposes rapidly, it produces nitrogen gas, carbon dioxide gas, there's some heat, so it's water vapor, and oxygen gas. That's why it's a good explosive, because it converts a liquid, with nitroglycerin, pure nitroglycerin is a liquid, into gas, just that fast. So that's where your explosive force comes from. But balancing that is no big chore. I mean, you can do that molecular, right? Just use your budgeting method that I showed you. 78 would probably be better balanced if we do it by a redox method. So let's do that one, 78. And that's chapter 4. Okay, so we're given the starting point of this. Let's see, let me move down here. Ki plus HNO3, nitric acid, yields KNO3 and NO and I2 and water. Okay. Now we could do this one molecular, but I think the redox method would make it a lot easier. So let's find out what our oxidation reduction or oxidation states are. So K and I are, this is -1, and this is a +1. Right? Alkaline metal, halogen, no big deal there. This one is a +1. We just found this one in a previous question as 5 plus. Right? Oxygen is 2 minus. This one's a +1. This one's still 5 plus. And this one's a 2 minus. What do we have here? Disproportionation. One of these nitrogens, or more than one possibly, went over here, unchanged, and some of them went over here, changed their oxidation states, right? Because this is 2 minus, that makes this one 2 plus. So it went from 5 plus to 2 plus. This one went from 1 minus to 0. Remember, all elementals are 0 oxidation state. Hydrogen is still +1, but oxygen, well, it's still 2 minus. So it looks to me like the oxidation reduction pair of reactions are between iodine and nitrogen. Okay? So let's say, what happens to this iodine? For each iodine, we lost 1 electron, right? To go from -1, get my head out here, -1 to 0, we lost an electron. So this is loss of 1 electron per iodine. And this one went from here to here. This one gained 3 electrons per nitrogen. Okay, now in the final analysis, the number of electrons that are gained or lost has to balance. Right? So we can't say multiply this times 2, that'll give you 3. We won't do it. Multiply times 3 here will give you 3 there, but then you're short 1 over here because you've got 2. So what that says to me is we had in the initial stage, we need we've got an odd and an even, right? So to compensate for an odd and an even, we need to even things out. Right? So how would you do it? Well, we can't multiply by 2 because that gives us, well, we could multiply by 2, but that wouldn't give us 3 up here. So cross multiply 3 and 2. I don't know, that it makes sense to me, but I'm not sure it makes sense to you. Let me try another tack. How do we get 3 electrons here? If we're going to have 3 electrons there, we need 3 electrons here. If we multiply by 3, 3 iodines here, then we have 3 halves here. Right, that's the only way you can do it. So, if we want to have whole numbers only, then let's multiply 3 here, which means 6 here, right? So that means 6 iodines times 6 equals 6 electrons. Lost 6 electrons in this fraction. So how do we get 6 electrons here? Well, we just need 2, right? 2 here and 2 there. Times 2 equals 6 electrons. Now we've got a ratio that gives us balanced electrons. Right? Now we've got to go balance the atoms. So what do we have to deal with here? We've got 6 potassiums. We need 6 potassiums. Right? So what does that give us for nitrogens, right? Remember, nitrogen was disproportionated, right? So we've got 6 nitrogens and 2 nitrogens. It's 8 nitrogens. So if we have 8 nitrogens there, that means we need 8 here. Okay? Okay, so let's reconnoiter. What have we done here? We've said instead of 2, we've got 8. All right, so now we've changed the electrons again. So that's 24 electrons. So how do we get 24 electrons out of this? Well, I'll tell you what, that's not going to work. I think the mental picture here is I've painted myself into a corner. What if we do 4 here? 8 hydrogens, 8 hydrogens, 8 nitrogens, 6 and 2 is 8, 6 potassiums, 6 iodines, 24 oxygens, 18, 20, 24. So the numbers balance. I mean, the numbers of atoms balance, but how about the electrons? Do the electrons balance? Is this a 5 plus? Did I do that right? Let me see if it is. 3 times 2 is 6 minus. 1 plus is 5 minus. Yeah, 5 plus. Okay, so that's right. We did this one already. That's right. So 8 times 3 is 24. And 6 is only 6 electrons. So there must be something else. Somebody else is losing electrons. You know, this is not working. This problem is best balanced the molecular way, isn't it? Because the redox doesn't seem to work. I don't have an answer for that one. Sorry. I'll take another look at it later and see if I can figure it out. But as far as that goes, it's probably better to balance this one molecular method using our budget. Okay, that's all I have, unless somebody's got some more questions. I'm also going to take that, load that Acrobat DC and see if I can figure out how to do subscripts and superscripts. There's got to be a way. And if I find it, I'll send everybody an email and give you instructions on how to do it. Otherwise, yeah, go ahead.
I was going to say, so we could just draw the subscripts in there then, because I figure that's probably going to be a little bit easier to go through that.
Yeah, do that. Unless I come up with an answer, plan on doing it that way. You've got till Thursday to do it, unless you're just chomping at the bit to take this exam.
I want to get it over with as soon as I can.
Okay. So if I find an answer, then you use it on the next one. Okay. That's it for now. We'll see you on Thursday, and pick up with gases, I think, is the next topic. That's a fun topic.
And then the lab, for the third lab, that's due next Thursday, correct?
Yeah, I think so. Let me flip over here. 24. Yeah, October 1st is when the waters of constitution and hydration are due.
And when we turn that in, do we just turn in the our formal lab report, and do we need to add?
Yes, right. From now on, you're finished with the informal reports with lab techniques. Everything from waters of constitution on is formal lab reports. So produce those in preferably a Word document, and attach them in a Blackboard.
Okay, and we don't need to add a picture of our lab notebook with that, or do we?
No, not for the report. That was just for checking your lab notebook. The reports are a standalone document. You don't need your lab notebook. Don't need any pictures from the lab notebook. Just the document, and you've got an example to work with.
Okay.
To give you a format. The first one's going to probably be a little shaky. You know, that's understandable. If you've never written a formal lab report before, I can understand that it's going to be a little bit shaky the first time. But second and third times, you'll start rolling, because you'll have sort of a template that you can go by. You'll have my reaction to your first one to give you places where you made mistakes, and you can correct those for the next one.
Okay, thank you.
All righty. Anybody else? I'm glad that was recording. I must have just left it recording to be safe. Okay. Well, I went almost an hour and 15 minutes over. That's about par for the course. We'll see you Thursday.
You have a good evening.
You too.